In this lesson, we will find the real zeros of a polynomial function. Our function is f of x equals x to the fourth plus 3x cubed minus 4x squared minus 10x minus 4. And we'll start by finding possible rational zeros. Possible rational zeros will be of the form plus or minus p over q. And here, p will be an integer factor of -4, which would be plus or minus 1, plus or minus 2, plus or minus 4. And q will be an integer factor of 1, which would be plus or minus 1, resulting in possible rational zeros of plus or minus 1, plus or minus 2, or plus or minus 4. We'll next use Descartes' rule of signs to find the possible number of positive and negative real zeros. To find the number of positive real zeros, we look for variations in sign of f of x. There's only one here, which tells me that we will have one positive real zero. The number of variations in sign of f of negative x determines the number of possible negative real zeros. So f of negative x here is equal to x to the fourth minus 3x cubed minus 4x squared plus 10x minus 4. And we have 1, 2, 3 variations in sign telling me there are either 1 or 3 negative real zeros. Let's determine the real zeros. Recall the possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4. And I'll just pick one at a time. We'll start here with x equals 1. To determine if x is equal to 1 is a real zero, I'll use synthetic division, dividing f of x by x minus 1. And in doing that, I will be looking for a remainder of 0. It looks like here we will have a remainder of -14. Not having a remainder of 0 tells me that x equals 1 is not a 0. Let's next try x equals -1. I'll divide f of x by x plus 1 this time using synthetic division. And again, I will be looking for a remainder of 0. And it looks like we have a remainder of 0 this time. So not only does that tell me that x equals -1 is a 0 of f of x, it also allows me to factor f of x into x plus 1 times 1 times x cubed plus 2x squared minus 6x minus 4. And from there, we'll look for another rational zero. This time, let's try x equals 2. And instead of dividing the whole function f of x by x minus 2, I'll just divide this factor of f of x, which is x cubed plus 2x squared minus 6x minus 4. Again, looking for a remainder of 0. We get a remainder of 0 this time, so x equals 2 is a real zero of f of x. And I now could factor f of x further into x plus 1 times x minus 2 times x squared plus 4x plus 2. My highest power factor is now a quadratic, and at this point I usually quit plugging in possible rational zeros, and I set this quadratic factor equal to 0 and solve for my remaining zeros. Unfortunately, this quadratic does not factor, and so I will need to use that quadratic formula, which is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Simplifying gives me remaining zeros of f of x of negative 2 plus or minus square root of 2. Okay, so in the end, I have zeros of x equals negative 1, x equals 2, x equals negative 2 plus square root of 2, and x equals negative 2 minus square root of 2. Each of these zeros is of multiplicity 1, and if you notice there is only one of these, x equals 2, that is positive. The other three are negative zeros, verifying our results from Descartes' rule of signs. Try this last one on your own. Determine the real zeros of the polynomial and state the multiplicity of each real zero. F of x equals x to the fourth minus 9x squared plus 4x plus 12.